In this talk, I'll introduce abstract neural networks and describe some fundamental theoretical results about them that are presented in our paper. Nowadays, deep neural networks, or DNNs, are commonly used in computer software. DNNs are a special type of straight-line program that operate on vectors of real numbers by applying alternating layers of linear and nonlinear transformations. Two of the most well-known applications of DNNs are image recognition and speech recognition, where DNNs have been responsible for significant accuracy improvements over the last 10 years. DNNs are also quickly being applied to safety-critical applications. The ACAS-XU DNN, for example, takes as input a description of an airplane and its surroundings, and provides a direction to the plane, such as whether to turn left or right. Of course, we want to ensure that these DNNs are safe to use. However, the large size and extreme nonlinearity of such DNNs causes standard verification approaches to fail. This has motivated research in scalable DNN verification. To get a better understanding, let's consider this DNN, which has one input and produces three outputs. Suppose we want to compute the output of this DNN given an input value of 1. We'll assign this input to the entry node on the left, then multiply its value by the edge weights to get the inputs to the nodes in the second layer. We then apply some activation function to these values, which is a nonlinear function that can differ between different networks. In this case, we'll output 0 if the node's input is negative, and just pass the input through otherwise. That produces an output of 1 for the first node in this layer and 0 for the second. Repeat this process to compute inputs to the final layer of nodes, and for simplicity, we'll use the identity activation function for the output layer to produce the values shown. So if we look just at the input-output behavior of this process, we can see that this DNN defines a function which outputs the vector 1, 1, 0 on an input of 1. When working with DNNs, it's often nice to think of them not as graphs, but rather in terms of matrices. Specifically, we can organize each layer of edge weights into a layer weight matrix. For example, the first layer has 2 edge weights, which we organize into the matrix W1. We can do a similar thing for the second layer, producing weight matrix W2. The DNN is then uniquely defined by these weight matrices, as well as the associated activation functions sigma1 and sigma2. Currently, to verify a DNN, you would input it directly into a verification tool, which either states that the DNN is safe, provides a counterexample, or states that it is not able to prove either. However, such tools can be very slow for large DNNs. We propose to augment this process for large DNNs via the use of abstraction. In our proposal, we start with 3 inputs: a DNN, an abstract domain, and a partitioning of the DNN's nodes. The partitioning and abstract domain will determine the precision of our abstraction. From these, we produce an abstract neural network, or ANN. This ANN is smaller than the original DNN, but soundly over-approximates its behavior. We then verify this ANN using a verification tool, and our soundness result guarantees that if the ANN is verified, then the DNN will be as well. For this talk, I'll focus on the first part of this workflow, namely how we soundly abstract a given DNN into a smaller ANN. In order to do this, we'll have to answer 2 questions. First, we need to define what exactly is an ANN. Then we'll need to explain exactly how to over-approximate a large DNN with a smaller ANN while guaranteeing soundness. In the rest of this talk, I'll define ANNs, describe our algorithm, and discuss its soundness proof. Whereas a DNN is a function that associates with each vector of numbers another output vector, an ANN will be a function that associates with each input vector a set of output vectors. We'll start by describing a specific instantiation of ANNs, called interval neural networks, or INNs, which were actually introduced by Prabhakar et al. Last year. Here's an example of an INN. It's like a DNN, except the edge weights are replaced with intervals. Given an INN, we can form an instantiation of it by replacing the intervals with a single scalar in each corresponding interval. Here's one example instantiation. There can be infinitely many such instantiations, so we'll let gamma INN be a function mapping any INN to the set of all of its instantiations. We now need to define the semantics of an INN. Recall that we want an INN to output a set of vectors, while each instantiated DNN returns a single vector. So we'll define the output of the INN on an input x to be the set of outputs of each of its instantiations on the same input x, as shown here. The first major contribution of our paper is generalizing this definition of an interval neural network to arbitrary numerical domains, such as octagons and polyhedra. To define such abstract neural networks, or ANNs, we associate with each layer some element AI of an abstract domain. In particular, we want the concretization of each AI to be a set of matrices. We then define a DNN instantiation of this ANN to be any DNN where the layer weight matrices belong to the concretization set of the corresponding ANN layer's abstract weight matrix. We'll similarly define gamma ANN to be the set of all such instantiations, and define the output of the ANN to be the set of outputs of all the instantiations. With this definition, you can directly generalize the notion of an INN to use any numerical domain, including intervals, difference-bounded matrices, polyhedra, and octagons. So far, we've defined ANNs. Next, I'll describe our algorithm for over-approximating a large DNN with a smaller ANN, and after that, we'll discuss the soundness of our algorithm. The goal of our algorithm is to abstract a large DNN n into a smaller ANN n sharp, which soundly over-approximates n. Specifically, we'll say that the DNN n is soundly over-approximated by the ANN n sharp when for every input, the output of n is in the output set of n sharp. Recalling the ANN semantics, what this means is that for every input x1 to n, there's an instantiation of n sharp with the same output on x1 as n. We'll start by describing the abstraction algorithm for interval neural networks introduced last year by Prabhakar et al. The key idea is that we want to merge nodes in the DNN together to create abstract nodes in the corresponding INN. In this example, we've merged both nodes in the second layer together to create an INN with only one node in the second layer. We then take the weights in the INN to be the weighted convex whole of the corresponding weights in the DNN. For example, the first green weight in the INN corresponds to the two red weights in the DNN, so we assign its edge interval to be the convex whole minus 1, 1 of the two corresponding DNN weights. We apply a similar process for all other weights. The one important caveat is that we'll scale each weight up by the number of upcoming nodes which were merged together. For this weight, we use the interval 2, 2 instead of 1, 1 because two nodes on the left of the weight were merged. So we should treat a single input from that node as counting for two inputs, one from each of the original DNN nodes merged together. We repeat this weighted convex whole process to get all of the other weights in the INN. Our paper generalizes this approach to work with any abstract domain, A. Suppose we want to abstract this three-layer DNN by merging the middle two nodes to produce the ANN on the right. Our algorithm will construct the abstract elements A1 and A2. Specifically, it'll construct A1 such that all matrices of this type belong to the concretization set of A1. Each of these matrices is formed by taking the original layer matrix from the first DNN layer, then applying some convex combination to the outputs because we merged the two output nodes of that first layer. This algorithm will produce an element A1 that includes all such combined matrices in its concretization set. Similarly, the algorithm constructs A2 such that its concretization set includes all of these matrices. Each one starts with the initial second layer weight matrix from the DNN, then takes a convex combination of the two input dimensions. Finally, we weight the convex combination by the number of inputs merged, exactly like with the INN algorithm. So here we've defined the abstract elements A1 and A2 in terms of their concretization sets, but we can turn this into a constructive definition by applying alpha to both sides. One caveat is that these sets are infinite, so we cannot just compute each member of the set and then apply a finite alpha function to compute A1 and A2. Thankfully, one of the key theorems in our paper says that as long as your abstract domain A is convex, you get the exact same A1 and A2 if you only use the extreme points. Most common numerical domains, such as polyhedra, octagons, and intervals, are convex. In other words, we can change the intervals in this definition to sets. So to compute A1, we only need to compute the two matrices in this set and abstract with alpha, and similarly for computing A2. So this gives a constructive algorithm for computing this corresponding ANN. We've so far defined ANNs and described an algorithm for merging nodes in a large DNN to construct a smaller ANN. For the remainder of this talk, we'll describe when this smaller ANN soundly over-approximates the corresponding DNN. We'll first gain some intuition by focusing on the special case of the interval neural network we saw before, then expand this into a more general argument. Let's walk through a small example to see this in action. On the left, we have the DNN we saw earlier, and on the right, we have an interval ANN formed by applying the algorithm in our paper to this DNN. Let's assume we use the activation function sigma h shown here, which can output 0 on a negative input and act like the identity on any others. Note that this activation function does indeed satisfy the weakened intermediate value property and always has non-negative inputs, so our sufficiency theorem states that the corresponding ANN should over-approximate the DNN. To understand why, consider any positive input x to this DNN. I'll claim that this valid instantiation of the ANN has the same output as the DNN on x. We can evaluate the DNN, finding that the input to the first node in the second layer is positive, so it gets passed through, while the input to the second node is negative, so it outputs 0. Then the final output of this DNN is the vector xx0. Similarly, on this instantiation, we have that the output of the middle node is x over 2, and the output is exactly the same vector xx0 as the DNN. The key here is that in the instantiation, the merged node here corresponds to these two second layer nodes and takes the average value of both of those nodes, which is then scaled back up by the final layer. On the other hand, if x is negative or 0, we can use this instantiation. We can perform the computation to see that the output of the DNN on a negative input is minus x0 minus x, and that we get exactly the same output from this instantiation. So for any input, there's an instantiation of the ANN, which has the same output as the original DNN. Therefore, we say the ANN over-approximates the DNN. Let's now recall the more general ANN abstraction, which over-approximated the DNN on the top left here with the ANN on the top right, where A1 and A2 were defined according to the two inclusions shown here. Suppose we have an input x1, x2 to the DNN. Following the DNN semantics, this input vector is multiplied by the first layer's weight matrix to get the vector u1, u2 input for the second layer. Then we apply the activation function sigma to get the output vector v1, v2 of the second layer. Finally, we apply the output layer's weight matrix to get the output y1, y2 of the DNN. For simplicity here, we've assumed the output activation function is just the identity. The ANN produced by our algorithm replaces the two weight matrices with elements A1, A2 of an abstract domain. To show that the ANN over-approximates the DNN on this input, we need to show that y1, y2 is in the output set of the ANN on an input of x1, x2. This in turn is equivalent to showing that there exists some instantiation of the ANN, which also maps x1, x2 to y1, y2. To do this, we'll first show that for any scalar u sharp between u1 and u2, we can instantiate the first layer A1 such that x1, x2 maps to u sharp. We'll then show that there is at least one such u sharp which maps to the average of v1, v2 under sigma. Finally, we'll show that there's an instantiation of A2 which maps this average to the final desired output y1, y2. The key idea here is that after each layer in this instantiation, we want to realize that average of the nodes that are merged together. Then, because the input and output nodes aren't merged, their averages are just the original inputs and outputs to the network, giving us the desired soundness property. Let's take a closer look at each of these arguments. The first thing we need to show is that for any u sharp between u1 and u2, we can instantiate A1 to map x1, x2 to u sharp. Recall that we constructed A1 to include all matrices of this form, so it suffices to show that one of those matrices maps x1, x2 to u sharp. We can write the output of the instantiation like this, and because multiplication is associative, the rightmost multiplication just becomes the output of the DNN, u1, u2 itself. Expanding out this matrix multiplication, we see that varying alpha allows us to hit any point on the line between u1 and u2. The u sharp is assumed to be between u1 and u2, so there's always some alpha for which the output is u sharp. Hence, for any u sharp you pick between u1 and u2, there will be some instantiation layer w1 of A1 that maps x1, x2 to u sharp. The next thing we need to show is that at least one of these u sharps gets mapped to the average of v1 and v2 after applying the activation function sigma. As we'll see later, this is not in fact generally true for all possible activation functions. Instead, we'll assume for now that sigma satisfies the weakened intermediate value property, which is defined in detail in our paper, but it's effectively equivalent to the desired fact. Thankfully, all continuous activation functions satisfy the weakened intermediate value property, and so pretty much all of the commonly used activation functions work with our argument. So now we've shown that we can get from x1, x2 to the average of v1 and v2 in the instantiation. For the very final layer, we want to show that we can instantiate A2 with a matrix that maps this average of v1 and v2 to the original output y1, y2. Again, we know that A2 was constructed to have all matrices of this type in its concretization set, so we just need to show that one of them maps the mean of v1, v2 to the vector y1, y2. We can write the output of any one of those concretizations like this, and canceling the twos gives us a slightly simpler expression. From here, we can use one of the key lemmas in our paper. Namely, if v1 and v2 are non-negative, then there is some beta between 0 and 1, for which the rightmost multiplication becomes the vector v1, v2. Essentially, from the mean, we can reconstruct each individual element using beta between 0 and 1. From there, we see that this gives us back exactly the same computation from the original DNN layer, hence outputting y1, y2 as desired. To give some intuition behind where this beta comes from, in this scenario you can take beta to be v1 over the sum of v1, v2 to see that the equality holds and that beta is between 0 and 1. So what we've shown is that under reasonable conditions, you can instantiate the last layer's abstract weights A2 to some matrix W2 which maps the mean of v1, v2 to the desired output y1, y2. And then we've also shown that there's some u sharp between u1 and u2, which maps to that mean under sigma. And finally, there's some instantiation w1 of the first layer's abstract weights a1 that actually produces that u sharp on an input of x1, x2. And so overall, we've shown that for any input x1, x2, there exists an instantiation of the ANN which produces exactly the same output as the original DNN. With some subtleties handled in the paper, what this argument shows is that if the activation function satisfies the weakened intermediate value property, and if all post-activation intermediate values while computing the DNN's outputs are non-negative, then the ANN constructed by our algorithm soundly over-approximates the original DNN. We may wonder if both of these conditions were in fact necessary, and it turns out they were. Specifically, if the activation functions do not satisfy the weakened intermediate value property, or if some of the intermediate values are positive while others are negative, then we can construct a DNN using these activation functions for which the corresponding ANN does not over-approximate it. While this may seem worrying, in the paper we go over some extensions to the algorithm which can support even DNNs that violate these necessary conditions. Let's first take a look at an example where the intermediate values do not necessarily all have the same sign. Here we have the same DNN-INN pair we saw before, except now we're using the identity activation function. Consider what happens when we give this DNN an input of 1. Now the first node in the second layer outputs 1, while the second node in that layer outputs -1, giving us mixed signs which violates the conditions. Let's look at any instantiation of the ANN, where here the weight A is between -1 and 1, and B and C are between 0 and 2. Then the output of this instantiation will be 2A, BA, CA, but we need this output to be 0, 1, -1, which then implies we must take A to be 0, but then all of the other outputs must be 0 as well. So there's no way we can instantiate this ANN to have the same output as the DNN. This shows directly how, whenever the DNN can have mixed signs, soundness of the abstraction algorithm is not guaranteed. Thankfully, in our paper we describe an automated process to rewrite essentially any DNN into an entirely equivalent one, which uses only positive values. Let's now look at an example using an activation function that violates the weakened intermediate value property. This is the same DNN-INN pair we saw before, except now we're using the activation function that outputs 1 for any input greater than or equal to 1 and 0 otherwise. We can compute the output of this DNN on an input of 1 to be 1, 1, 0. What we find from any instantiation is that no matter what the input to the middle node, its output will either be 0 or 1. But then the first output node will be either 0 or 2, which cannot be the desired value of 1. So the takeaway from this example is that if your activation function has essentially big enough gaps, then soundness is not guaranteed. The workaround we propose in our paper for this is to effectively lift the activation function to a set-valued one to fill in those gaps. But it's really important to note that this is not a very common thing to run into, because any activation function with these gaps would be discontinuous, and so you'd have trouble even applying gradient descent in the first place to train such a DNN. In this talk, in our associated paper, we define abstract neural networks, or ANNs. We presented an algorithm for soundly over-approximating a large DNN with a smaller ANN, and we described necessary and sufficient conditions for that algorithm to be sound. There are two main areas of future work building on the foundations laid out in our paper. First is the problem of efficiently verifying an ANN once it has been constructed. One proposed approach for a special case of interval neural networks was described and evaluated by Prabhakar et al. Last year. Extending such an approach to octagon and polyhedron neural networks would be an interesting direction for future research. Another question is what to do if the ANN cannot be verified. In this scenario, we may want to refine either our abstract domain or the partitioning used. For example, instead of merging all the nodes in the second layer together, we might only merge half of them. Our work lays strong theoretical foundations for this kind of future experimentation and applications in the area of abstract neural networks. All of our source code is available on GitHub at this link.